suppose you consider there's a ball, and of course we make this ball A very big, like this, and then of course carries the initial velocity VA1, like this, right? Now we're going to say that suppose it's actually running like this, and well, let's make it more realistic. Suppose it's a either a vehicle or a big ball rolling like this. Maybe we just consider that like a tire. The tire is just rolling, and somebody got really good skills and try to get it running without falling down to the curb side. But there is a door like this, a gap, right? You know that because the gap is smaller than the size of this ball or a tire, whatever you want to consider it. To some point, this tire is going to hit here. It's not going to get through because it's smaller. The gap is smaller than the size of this ball object. Correct? So at the moment, this rolling object A is going to be stopped here, but it's not going to be, it will stop here because there's a force provided by the door, and this force is not applied through the center of gravity. Is that clear? Right? Because the center is here, this is G, and if you project it, the force must be applied horizontally, of course, in this case. And the velocity of this object is projected like this. There's a gap. That means these two, the force provided by the door and also the velocity component of this ball or the tire, they are not aligned. This is the problem, what we call eccentric impact. And so how do we solve this kind of problem? Well, we will solve the problem by what? By finding at the impact perpendicular to the impact surface, what is the fact that can change the initial velocity of the object. So that's the purpose for example 30. Right. Now in example 30, let us consider there is a support, something like this, and there's a wall. Now, suppose that this wall actually hangs a disc. And the disc is, its initial position is right at the interface, or let's put it this way. Suppose you hang a disc, and this distance is from the support. You can call the support A to the point of contact B. So this distance happens to be the radius of the disc. So you know that if I'm trying to hang a, disc like this, and that means I'm going to move this vertically static disc very slowly to the wall. So at the moment that when the disc touches the vertical wall, there's no force acting on this interface because it's exactly the same. The distance from A to the wall is the same thing as this dimension of the radius of the disc. So that is the initial position of the disc. Now what we're going to do here is to lift the disc. Say that we're going to lift it by 30 degrees because this support here is a hinge. It's a hinge point here. And of course, obviously, this is the center of gravity. And then we're going to lift the disc by 30 degrees. So how do we know 30 degrees? Well, 30 degrees is measured from the vertical direction to here. we say we're going to move it by 30 degrees. So this is 30 degrees. All right. Can we do it? Of course we can do it because it's a hinge. So you can certainly lift it by 30 degrees. So instead of drawing this, the shape of this moved the disk, I don't want to destroy your understanding here. But you can imagine that, let's use the center of gravity to describe this change. So suppose the radius of the disk is 150 millimeters. And because I said that this radius is the same distance from point A to the wall. So that means the radius R here is exactly this value. And this value is 150 millimeters. And certainly you want to convert it to standard unit. What is the standard unit here? Standard unit must be meters. Therefore, 150 millimeters is just 0.15 meters. So that means the center G to this point B, point of contact, is exactly the distance from point A to the wall B, from this wall, which is 0.15 meters. And of course, that means this is the original position of the center of gravity of this disk. And after you move it by 30 degrees, we can denote this point as G prime. We can do it, right? So you can imagine that I'm going to use G prime and G to denote the changed position and its original position of the disk. And we know this angle is 30 degrees. So what is the question? The question is this. Suppose we lift the disk by 30 degrees, this value here, and you know that the coefficient of restitution, E here, is 0.6. That means we know that for the type of the material used for this disk and the type of the material of the wall, we know that from previous study, this coefficient of restitution is 0.6. And remember that this coefficient actually regards the interactions between two different kinds of materials. So it's not necessarily about whether which material is stronger than the other. We don't know that. We just know that between these two materials, and this coefficient is 0.6. And we also know the weight of the disk, or the mass of the disk. So let me give you the mass. The mass of disk is 15 kilograms. So what are we looking for? We want to know that, and this is the angle. So we're going to call this is the measurement, theta. We want to know that after lifting the disk by 30 degrees, and of course there's a gravity, so we're going to release it. And once releasing it, what happens to the disk? The disk is going to spin, right? Because of gravity, it's going to swing back to its original position, but this time it's going to carry a angular velocity, which means that it's going to run into the wall. Correct? Once it hits the wall, impact occurs, which means there's going to be a rebound. There will be a rebound force driving this disk to go back, to move in the reverse direction. And when that happens, of course, we know that, do you think that the disk is going to return to its original position, 30 degrees? Do you think it's possible?
Slightly less, probably.
It's not going to be the same, right? It will not return to the original position, 30 degrees. Why? Because of this. Now, if you assume coefficient of restitution is unity, if you assume that, that means linear momentum will be preserved. And in that case, from this kind of analysis, if you assume E being 1, then our analysis will predict that the disk is going to go back to its original position. But in any case, you know that's not going to be, that's not true. And realistically speaking, why? Because they are sources of friction, which will dissipate the energy. So you can imagine that by moving the disk at 30 degrees and releasing it, moving this one, that means the G is going to move up. So this increase of elevation at the center of gravity is the little amount of potential energy you store in the system. So releasing the disk is the conversion of potential energy to kinetic energy. Now, at the point of contact, this is where the impact happens. This is where the EBIT doing its own business. Because E is now 1, that means some of the energy is going to be consumed. But realistically speaking, there's air friction, right? And there's also friction at the support, which is why you will never expect that, realistically speaking, you will never expect that this will actually begin to go back to 30 degrees. So what we need to determine is what is after the impact, find out what is the maximum angle. That's what we are trying to determine. What is the angle?